Yeah. All right. Well, happy Wednesday. So, I mentioned later today the chancellor's having like an all-staff meeting with faculty and staff around key performance indicators, and I thought it was cool. One of them is, I know it's really tiny. I'm sorry. Let's see if that's any better. Nope. And so something they'll be measuring. It's not measured yet, but will be measuring here is at least one faculty or staff member cares about me as a person. Will be in the 2022 RNL Student Satisfaction Survey. So I don't know who that goes to, who gets to take it, or what. But I thought this was cool. They're going to measure that. I found that interesting, and the chancellor is saying this is really a key performance indicator of how we're doing as a university campus. And a bunch of other things too, like graduation rate and whether or not you get a job in your field and other important things too. But like, I thought this was neat here. So my anecdotal evidence, I did a quick little survey in the one Discord, is this is not going well. Just okay. I don't know what to say about that. So I get it. I guess college is weird. So for today, we have to finish searching and sorting. We have to talk about project 3. We have to talk about the final project. So we're almost done with searching and sorting. So if you don't mind, I'll do that first because we had like one last thing to finish because you guys just let me talk and talk and talk. And thank you for reminding me to shut up when class is over because I'll just talk forever because I like to talk. So we were doing our insertion sort. And the idea here with the insertion sort is that we go and assume the first number is sorted. And then we go through, I don't have my chat open. Let me open up chat here. Then we go through and say, okay, the next item, let's insert you into the sorted list portion. So if it's already greater than, it's done. But if it's less than, we start backing it up until we find something it's no longer less than. And now it's in sorted order. So what's good about the insertion sort is the best possible time if it's already sorted is just O of n. We just look at each item and say, okay, are you greater than the thing before you? Yes. Nothing has to change. Where with our selection sort, the worst possible time is, or the best possible time is still n squared because for every n, we have to look at every n item, right? Because we're building out what is the smallest item. Great, swap. What's the next smallest item? Swap. What's the next smallest item? Swap. What's the next smallest item? Swap. So we're still looking at everything no matter what. So insertion sort performs a little bit better than our selection sort just because it doesn't have to do that extra work. And so these are the two basic sorts we look at that are pretty easy. Zybooks also covers merge sort and quick sort. Those are a little bit more complex. You'll get more into those in data structures, algorithms, and analysis, pretty sure, where we look at some of those. So the merge sort is nice in that it's more of a divide and conquer process. It's going to break apart, do a bunch of smaller sorts, and then put them back together into a bigger list. It can be a little bit faster, which is pretty cool. There's some fun sorts. The most interesting one out there that I know of is the radix sort. What's fun about the radix sort, it's like a good list here, is that it does not compare numbers directly. And if you just think about that conceptually, like, how do I sort something if I never compare? Is this number greater than or less than? Like, whoever came up with this, honestly, I think is like kind of a genius. So instead of comparing, we put them into different buckets. So if I know all of my numbers are integers, I know at most I'm going to have 9 digits, right? So I'm going to make 9 different buckets. And I'm going to bucket the numbers based on their leading digit. So all the numbers with a leading 0 billions, go in the 0 billions bucket. Then all the numbers with a 1 billion digit go in the 1 billions bucket. All the numbers with a 2 billion digit go in the 2 billion bucket. Then I take the numbers and put them into a bucket based on the hundreds millions digit. And then on and on and on and on. So what you're going to do is you're going to take all the numbers with a 0 leading digit and then go into the next bucket and say, give me all the numbers with a 0 next leading digit, and all the numbers with the next leading 0, next leading 0, next leading 0, until you get all zeros in just ones places. And then I just take them out in order. Give me the 0, give me the 1, give me the 2, give me the 3, give me the 4. So you never have to compare numbers directly. You just put them into buckets and you pull them out of the bucket in the right order. It's just a fascinating way to sort things. Was super cool. to look at that one. But for our insertion sort, so starting at 1, because if you only have one item at index 0, it's sorted. Nothing has to happen. So we're saying, well, my index to check is greater than or equal to 1, because I'm going to check the number that comes before it to see if I have to swap. So I can't get to 0 because you can't check a -1 index. So the last possible sort here is going to be this one. So if I'm less than, right? If I'm less than, then this is going to be true. I'm going to swap. So I'm going to have my int temp is equal to my numbers at the index to check. And then I'm going to have my numbers at index to check is equal to this one here, right? We'll change it, and then we'll put it back. And this one equals the temp, right? Go through and swap. So store this number, overwrite that number, put that one in on top. Then take our index to check, minus minus, go down by 1. So now I'm going to say, okay, well, I've slid it down 1. So like when we looked at, hey, if I had, this is the sorted order. If we had one that wasn't sorted, we had 21, 10, 3, and 23. This one's already sorted, so we're going to check this first one here. Okay, so 10 is less than 21, and index to check is 1. This is good. It will run. It will swap these two, and I'll have 10 and 21. Now index to check is 0. My loop stops. Okay, so now index to check is going to be 2. Let's look at this one here. Is it less than the number that comes before it? Yes. So let's swap. So this becomes a 3. This becomes a 21. Index to check is greater than or equal to 1, and it is less than the one before it. Swap again. So now we get 3 and 10. Now we're done because we got to index 0, no longer greater than or equal to 1. Then we get to index to check is 3, right? Because we're looping through index from 1 up to size here on the outer loop, checking each one. So this one will progress it. This does the swapping back as far as it needs to go. So once we get to 23, it says, are you less than the number before you? No, no swapping has to happen. We're done. So this one's fantastic. So, and like if you have a number in the middle here, if we had a 15, now our index to check is 4. Is it less than this index? Yes. So let's swap 15 and 23. Is it less than the thing before it? Yes. So let's swap 15 and 10. Or I'm sorry, 15 and 21. Is it less than the thing before it? No, it stops. It doesn't have to get all the way back to index of 0. We either get to index of 0 and we've taken it as far to the left as we can, or we stop when there's something no longer bigger than us behind us, right? When we are no longer less than the number that comes before us. So that's the insertion sort. So this should work with numbers here. Okay, so you guys will have the fun of doing this in lab, and I'm going to be honest, you can copy paste from online, but please don't, because then you've gained nothing. Where instead of doing this with integers, we'll do this with a template. So any type that you can compare less than with, is this type less than this type, you can insertion sort or selection sort, right? Because all we're doing is taking less thans. That's all we have to do here. So we should be able to sort anything that is comparable here. So as long as we've implemented a less than, we can sort. What gets to be fun then is if we write a custom class and we override the less than operator, now we can sort our items. That's all we have to do. If you tell me how to compare one item to another and tell me which one is less than, I can sort, right? Whether or not that's going to be like the number of characters in a word, if you want to do the length of word sorting, or if it's grades, you want to sort by the numeric value of grades, or if you want to sort by student ID number in the student class, sure, we can, any way you want to define how you compare this object to this object, what is less than, you can. And you can sort them with these basic sorts. And what's fun is the algorithms will actually work as well, the built-in ones. You don't need to write your own. Writing your own is a little silly, but it's a good exercise because it's a good practice, again, kind of conceptualizing how these things work, working through it here. And then if you've written it, you'll understand how it works better. And right, really the whole goal here is our algorithms analysis and knowing which one is faster at what. That's why we study these. So when you go to solve a problem, right, it used to be, and it still mostly is the case, if you get it done, you get the points. That's perfectly fine. That's all we're looking for at this first level of learning how to code. Once we've progressed a little further, we've expanded our toolkit. Now what we're looking at is, did you solve the problem and did you solve it efficiently? For most of our purposes, we could care less, right? We're not doing anything large. We're not doing anything at the million times scale. We're not doing anything with millions of items in memory. So efficiency doesn't really matter for us at this point. So we just want to focus on how do I solve problems. But once we start developing our skills and our tools and being able to solve these bigger problems, efficiency matters. So we can start looking at, well, what is faster? My arrays are really fast, right, at getting things directly out by index. So if I'm going to read things at different indexes, it's really fast. If I'm going to be inserting things and all over the place in the list here, that's generally pretty slow, right? Our linked list performs better at inserting at given positions because it doesn't have to do the copying and swapping and shifting everything over every time. So once we start scaling up and doing things more and more and more and more, we're working with larger data sets, that efficiency matters. And that's why we study it, because it is important. Okay, so I think we're good with insertion sorts. We could try and make sure it works, but we got to move on to other things here. So I guess we should try. That was bad. We should try it here. So we want to insertion sort our numbers list here, make sure that works. And then are we taking a reference here? Because last time I screwed that up. Yeah, we're taking a reference. So last time that broke on us. We'll see if it works now. All right, so it looks like it sorted it properly here, right? Because we have them in the correct order when we go and find them with our recursive binary search that we wrote last time. They appear to be coming out in the correct order. Okay, so I feel pretty good about that one. We can commit that to GitHub. So that was almost done. So thank you. If I didn't have low sugar on Monday, I think we would have had time to finish that, but it was okay. I had a Coke. We get to have a chat about random other things, which is good too. If the only thing we ever talk about is like course content, we're missing a little bit here. We'll be honest. Like there's some value in that other conversations for sure. Yeah, there's a lot of miscellaneous stuff for sure. That's important. Insertion sort for sure. I mean, if all you wanted was the content, you're probably not after a university degree anyway, because you can just go learn all that stuff. There's YouTube tutorials out there to learn how to code. So, I mean, I get you get a piece of paper, and a lot of HR companies want that piece of paper. That's a whole other issue too. But you know, if the only thing you're looking for is technical content, you don't need to be here. Right? You can go find it online. But hopefully, you get something more out of it. All right, so let's take a look at our project. So this was our commander project. This one was a little crazy, and that's okay. We're putting together a lot of our concepts here, kind of pull them all together here with pointers, with copying, with deep copies, with managing items in a list, with sorting things. So a lot of different things were happening here. I had lots of questions around add creature. So a bunch of people didn't finish it, and that's okay. It's not the end of the world. So the add creature function, if it only added a single creature, that's half the points, right? If it added the whole chain of creatures, that's the other half the points. And this is where most people got caught up here is, how do I deep copy this whole chain? Well, what comes next? 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 Our code needs to handle that because it's not a deep copy if I just say, oh, your next creature, I'll take your pointer, and now I have two pointers at the same location. That's not a deep copy. That's a shallow copy, right? So this idea of how do I copy and copy and copy and copy and copy while allocating new memory is the tricky part here. Okay, that was the goal with this assignment. So get a chance to actually get into some of that nitty-gritty piece here of doing that. So let's make our creature class first here. So we'll have our class for creature. Creature, it has a private section, it has a public section, right? So it has, what do we have, an int for strength. I'm sorry? Not colon, yeah, thank you. I like Python. Python likes colons. So an int for strength and an int for defense, and then a creature pointer for the next creature. Right? Those are our attributes for creature. Okay. I had said a positive integer. Some people went through the trouble of doing sanity checking and throwing exceptions. That's awesome. I wasn't expecting that. I was just telling you like it's an integer type. So I apologize if that wasn't clear. Good for you. You did a good thing. I'm assuming you already knew how to do that. I try not to like throw in so much other stuff all the time, but that's okay. So now we need a constructor, right? How do I make a creature? So creature constructor. If you give it these values, we'll take them, right? Strength, int defense, and then how about a creature pointer for next creature? Now this one, we might not always know what the next is. So this might make sense to default to a null pointer. This is like a for loop here. What's going on? Okay. Is this font really large? I feel like that's really large. Like this is already kind of small here. Anyway, all right, so I can set my this strength to the strength. I can set my this defense to the defense, and then if I just accept the creature here, I might also have a shallow copy. That's probably not what we want, right? Because now I've got 2 pointers pointed to the same location. Like if we want to be doing deep copies of things, we want to manage our deep copies here. So if it's null, it's perfectly fine. So we can say, hey, if my next creature is equal to a null pointer, then we're perfectly fine. We'll set my this next creature to the null pointer, essentially. That's okay. But if it's not, else, oh my goodness, then I need to do a deep copy. Because otherwise, right, we have that shallow copy, bad things can happen because now I'm pointing to somewhere else that you still have a pointer to. When you go change your attribute, it changes mine, which is probably not what we want here, right? So to do that deep copy process, if it's not null, I need to go and allocate new memory. Right? So by this new next creature equals a new creature, given the next creature's strength and given the next creature's defense. Right? Now I have a deep copy. But what if there's another next? Right? What if this next creature has a next creature? What if that next creature has a next creature? What if that next creature has it? I don't want to say if this or if the next creature's next creature does not equal, like you don't want to go down this rabbit hole. That's not workable because it could be, we don't know, it could be 1,000 creatures. I hope it's not, but right, we don't want to have 1,000 different if checks here. Like that's nonsense, right? So we need to do some sort of process to be setting all these up. So what we really want is something that will walk that chain, like when we traverse our linked list. We have, here's the current, give me the currents next. Now current becomes the currents next. Now current becomes the currents next. Now current becomes the currents next. On and on and on, putting that chain together. Now the other problem is I can't just set my next creature, because now it's going to be my next creature's next, or my next creature's next creature's next creature, and on and on and on. So I need 2 different pointers that are going to walk simultaneously and say, okay, this one will equal this one copy to this one copy to this one. So we can do that then once we have a next creature here, right? So I can have this is my current, I don't know, or maybe a creature pointer. This current creature is my this next creature. That's the one we're currently working on, right? So if the next creature has a next, right, we've copied it with our deep copy here. Now we're going to say, does it have another next? And it'll become the next of this one here. And then I'll have a creature pointer for the, I don't know, the two copy next creature equals the next creature's next creature. Right, so I've done my first copy. So I have mine, and then if theirs had a next, I've copied their next. Now I'm looking at my last creature right now, right? And maybe we should say the current last creature or something. This is current creature. Maybe we should say this last creature, right? So this is our last creature in our chain of creatures. And then this is the 2 copy next creature is their next. And we can say, while my 2 copy next creature does not equal a null pointer, I have to start making more copies. So I need to copy it from the 2 copy next creature to my this last creature's next creature, because I have to allocate new memory. So I can say this one's next creature equals a new creature, given the 2 copies strength and the 2 copies defense. Oh, no, that's a semicolon. Then both of these need to walk, right? Now that my this last creature has a next, it can move to the next one. This last creature's next creature. Right, now this exists. It won't be a null pointer. Then my 2 copy next creature goes to the 2 copy next creature's next creature. If that's null, we stop. I no longer have something to copy. If it's not null, there's something I need to copy. Sure, let's go copy it. We keep on going. So we can actually skip this first part as well. Right? This first copy, we don't necessarily need to do this, which is nice. Right? If we wanted to shortcut this, because it's the exact same process here, we can start the last creature as this, and the next creature as the next creature. And then this, really nothing has to change. Right? It's not too big of a deal here. And we can set it to null pointer regardless, and then we can check to see if they have another one to copy here. So we can sort of clean this up a little bit here and just say, okay, let's go do these copies. So we'll assume it's null for our next creature. And then my last creature is currently me. It's my this pointer. Okay. The 2 copy next creature is that next creature's next creature. Or the next creature, right? The creature we're copying, it's next creature. If that's not null, make the copy and then walk. If it's not null, make the copy and walk. If it's not null, make the copy and walk. So this way we can deep copy all creatures in this chain using those 2 pointers that just walk and walk and walk and walk. Right? And we have to be behind, so we start with this because we don't have a next yet. It's null until we go and allocate new memory here. Right? Does that make sense for how we're getting the deep copy here with the creature? Okay, awesome. And then we need some gets and sets, right? So public gets int for get strength returns, oh, not public, sorry, returns this strength, and a int for get defense returns this defense. Now we probably also need a way to get the next one, right? Get the next creature. So a creature pointer get next creature returns this next creature, right? Give them the pointer so we can get access to those. So we have our public get methods. Now, nothing ever really sets here, right? We could have a set next creature if we wanted, a way to interact with set the next creature. We could do that, right? We could have a void for set next creature. So if we've allocated memory, we might want to delete it. Otherwise, we might have some memory leaks. Oh, I'm sorry, given a creature pointer, next creature. Now, this gets to be a little tricky here because we probably still want to do the same deep copy process, right? Well, that's actually pretty easy here. We can just do this, right? To copy the next ones over. So we can just call set next creature given the next creature, right? You don't want to have the same code twice. Otherwise, you feel bad about yourself. So if this is my process to set the next creature, sure, we'll just do that in our constructor. We'll set the next creature. If you give me a different next creature, we'll go and set it. Now, the only thing we might want to do then is delete our current pointer, right, to make sure we're deallocating that memory. And that has to be a little bit messy here because if we don't go all the way down the chain and delete all the chain, it's not like an array where I can say, hey, delete the array. It's not an array that we've allocated. It's individual ones. So you can go through and delete everything down the chain if you want here. So we can say my creature pointer, the next creature to delete equals my this next creature. And then we can start looping through this, deleting those as we go. Right? We can say while my next creature to delete does not equal null pointer, we need to go get the next one, and then we can delete the previous one, and loop and loop and loop and loop. Yeah. So yeah, so we could add the destructor. So the only issue with, like, if we're adding a destructor, then we probably also need the copy assignment operator and the copy constructor. So that could be a good way to do it there as well. Yeah, and then it would be removed and would destruct itself, right? When we replace it here. Actually, no, we still need to delete it, right? So this logic here would just happen in the destructor, right? At that point, where we go through and loop and delete all the next ones here. So you could. So if it's not null, we're going to have a creature pointer temp, I guess, equals the next creature to delete, next creature to deletes next creature, and then we can delete the next creature to delete, and then our next creature to delete can equal the temp here. Right, so if we hold on to that next pointer, then we can delete the current one and then move to that temp one that we just had. Because if we delete it, then we can't go to the next one to delete the next one here. So this should make sure we're cleaning up after ourselves, or like a destructor is probably a good idea as well. We got creature. Right, so creature needs to handle that chain of creatures is the big idea here. So, all right, now we can do our commander class. We can add a new commander class. And then commander, commander, add the private section and the public section. It had an int for hit points, right? And then it had a creature pointer for the first creature. So we got to include our creature. Oh, creature, there we go. Include creature. Has a creature pointer for first. And then that's really it, right? Sure. Cool. So those are our attributes. So then our commander constructor then doesn't need to do a whole lot. Doesn't need any arguments. It's just going to take my hit points, set it to 40, and then first set to a null pointer. Right? Give defaults. The constructor's job is to give your attributes values. So we get some good default values. Okay. Then we needed an add creature method that makes sure we get the deep copy, not a shallow copy, and then ensures they're in sorted order. So our creature method, adding a next creature, had nothing to do with sorted order. We just copied everything, right? We just took it. So commander then will have to go make sure that we're in a sorted order when we go and add a creature, right? So let's try that. So we'll have a void for add creature given a creature pointer for the creature. Right, so if you give me the pointer, I can go and take it here, making sure we have a deep copy. Right, so if I have the pointer, we're in pretty good shape here. Right, we can make a creature. It can know the next one here, but we don't want to just take the creature. Right, we don't want that shallow copy. So that's where if you had the copy constructor, it would be really nice. I could just make a new copy of it here. Right, so we could go through, we can make that copy constructor if we wanted. So we could have a creature given a constant reference to a creature that our copy constructor. Creature, constant creature. Oh my goodness. Spelling it wrong? No. Creature. This strength is equal to the creature strength. Oh, that's right, my variable name for other. Constant creature reference. On the wrong side. There we go. I always get those on the wrong side. So we'll take the other's strength, take our this defense, set it to the other's defense, right? And then we would set our next creature, given the other's dot next creature, for our copy constructor. Right, this should copy all of them, I think. And given our set next creature, given the pointer goes and makes the copy of all the next ones. So now we should be able to say our first equals the creature. I'm sorry, first equals a new creature given the creature. Use the copy constructor. Not like, dereference our pointer, right? To give it a reference. Sure, or we could use that copy assignment operator. Would also work as well. So once we define that one, so that was a creature operator equals, given a constant creature reference other, something like that. So that one could work as well, right? We could just assign it then to the dereferenced creature, right? Or no, yeah, we don't want to keep the pointer. Creature.
Like you return.
Yeah, we got to return this when we're done, right? Yes, we should return a pointer. I always have to go copy this stuff because it's nonsense. I think that'll do it then, right? If we go and do creature pointer. I'm sorry? This is the pointer. I can remember how we did this before. This. Oh, dereference. Yeah. Okay. To reference. Yeah. So you return the reference of the dereference to this. Thank you. Yeah. That's why I always go copy that. Cool. So we can do this. I think we wanted that delete. So we could add our destructor as well then, right? So if we have a creature destructor, goes and deletes all this stuff. This will delete all the next creatures in that chain. Right, so then I think we're okay then, skipping all that because we moved it to the destructor. It'll go out of reference and should get destructed. All right, so for our copy operator, we're going to check to make sure that what the other does not equal this first, does not equal not equal the not equal this. What did we do before here? We did these before. Pointers. It's not giving me that option. What is it here? The point, yeah, that was when we did. My goodness. So, pointers. I can't read today, folks. Thank you. So we did that in like student, right? We have the destructor. Do it in gradebook. This does not equal the reference of gradebook. The reference of other, isn't it already a reference?
You did other, it's not equal to this.
Oh, it should. It's same direction, right? So this does not equal the reference of other. Okay, so if the memory we're pointing to is not the other, sure, go for it. Then we can delete our next creature to make sure that triggers all the deletes right down the chain. Then we can go do our copy. This strength is the other strength, this defense is the other defense, the next creature is the other next creature. Then we can return this. We're done. So there's a lot happening in creature, right, to make sure we get deep copies, because that's important. Right? We don't want to have a shallow copy, because then if you go change something, it's messed me up. Or if you go delete that, it's messed me up even more. And that's really the more of the danger here. If it gets deleted, we don't have a copy. So we should just be able to do our copy assignment operator here and just take it because we've done all that hard work there. Then we need to go and sort. Right, so now we need some sort of way to sort creatures. So probably some sort of private function here is ideal. I'll have a void for sort creatures. Right, and we wanted to sort in the highest strength, highest defense first. So go through and find the highest defense creature, right? And then add the next one and add the next one and add the next one. So we need to go find which one is the highest. So our creature pointer, the current creature, equals my this first, start at the first one, and we need to go find which one is the highest. Now, we want to take each creature at a time, and we can put it into the sorted order, essentially, as we do these. So if I find the highest defense, I want that to be first. And then I take the next highest defense, make that one the next one, the next highest defense, the next one, the next highest defense, the next one, next highest defense, the next one, on and on and on as we go, right? So we need a way to add. Oh, I'm sorry. So this only works if our first is not. We're not done yet. Shoot. So if first is equal to a null pointer, because we need to be in a list here first. So if first is a null pointer, add it there. Otherwise, right? Then what we want to do. So we've got a couple options. Probably the easiest way to go about this here is we can say, I want a new creature here to be a copy of this one, and then I want to set. I've probably put it at the end. Is probably easiest. So go find my last creature, add this one to the end. If we added it to the front, that could also work, but we don't want to override any of its nexts either. So we got to find like the last creature. So we'll have our current creature, creature pointer current equals my first, and while current dot next creature get next creature does not equal a null pointer. So as long as I have a next, I need to keep on going. Current get next creature. As soon as my next is giving back a null pointer, now I want to go and set its next. So when I'm done, then I can say my current set next creature given the creature. Right, so this will go to the end of the list and add on this creature to the end of the list and a copy of all of its nexts. Right? So I've maintained my list of creatures. I've added in their list of creatures, or just 1, 2, however many creatures it has to be. Then I want to go sort my creatures here. Okay, so for each creature, then I need to go and put them in a sorted order based on defense and then based on strength, right, if they have the same defense. So I kind of want to build out my own list of creatures, right, where I can have my first one and then the next one and then the next one and the next one and the next one and the next one. I think that'll work out pretty well. Let's see, if we go set next creature. Yeah, so setting next should just work. So we want to find the one, so for each one of these, now we want to loop through to the end to find the one with the highest strength and set that one, and then find the next highest strength, the next highest strength, the next highest strength. Let's see, but we never remove them from our list, do we? Let's see, that's kind of annoying. We want a way to sort in creature. Yeah, it might be easier to sort in creature.
Yeah, but I mean, you add like more creatures.
Yeah, I think having commander sort them makes more sense here. So we got to find the highest defense first, make that be our first, and then we go through the rest of the list here. Oh, okay, this is a little bit annoying, isn't it? Let's see. So while our current creature does not equal a null pointer, we can loop through. Eventually, we'll take current is the current's get next creature. We can walk through. So when we set next, and when we set next, we're getting a copy. That's kind of annoying. So I think we'll have to set next to null and make a bunch of copies. Bless you. So we want to find the one. Let's see, we have the highest strength. So an int for highest defense. We'll assume it's 0 until we find otherwise. So we can check if my current creature's get defense is greater than my highest defense. Nope, highest defense. Then we'll have a new highest defense. Doesn't tell me what the highest score is, but now we actually need the creature pointer though, don't we? I guess I want the creature pointer with highest defense. We can make a creature here, given zeros. We can do that.
You just create like a new creature like first, like a different one.
It would, but then it's going to copy all of the other ones down from there.
So then it would copy it.
Yeah, so we want to find the one with the highest defense and set it as first.
And you copy the new one into the first and then rearrange it. That makes sense. So you make a new like list.
Yeah.
And it would start at null. And then you go through the entire current creature, you throw them all. And then you'd find the highest, and you'd add that to the first of your like the one that's temporary technically.
Mm-hmm.
And then you take that off, and then you create, and then you go again, and then until your first is basically null.
Yeah.
Then you
empty it out and reset first.
You just do that equal to your first, and you just copy it over.
Yeah. So we to do that we have to find the highest defense one, right?
Yeah.
I think that's what I'm trying to do here. So we're going to find the creature with the highest defense to find the highest one. So this way I can use a creature pointer to go find the one with the highest defense. Now removing that one's harder though, because we don't have the double links, which is the problem. Because we'd want to remove it, you have to be the step before it to jump over to its next. I think it's doable. Yeah, it's probably doable. So if we make a new creature, then creature pointer, this will be our new first creature. Right, so we'll go find the one with the highest defense. Then we can go and set that new first creature to the creature with the highest defense. Oops. New first creature equals the creature with the highest defense. But then we want to get rid of the remaining ones after that, right? So our new first creature, set next creature to a null pointer, right? To get rid of all of its things that come after it. Then we need to remove that creature from the original list, right? Okay, so let's see. So we'll start with first, go with the highest defense, new first creature. So this one has to be outside of all of this then. And that's going to happen while this first does not equal a null pointer. We want to set it to the next one though. So I think we want to add it to the last of this chain.
Yeah, so
if our new first creature is a null pointer, then it can just become this one. If it's not, then we need to go add it to the last of that one. So then our current pointer, current new first, or current new, I guess, is the new first creature. And while my current new is not next, right? Get next creature does not equal null pointer. Current new equals current news. Get next creature. When that's done, my current news set next creature is the new first. I guess not even new first creature. Oh no, creature with the highest defense. Right. Be the creature with the highest defense. And then current news. Get next creature. Set next creature to a null pointer to remove all of its things that come after it. And we still need to take it out of the list though. Oh my goodness. So once we've had it, then we can go through and take it out of the list then. So while we need one more creature pointer, current equals this first, and while I just want to check we can check the first one first. If my creature with the highest defense is equal to my this first, then my this first equals the this first's next. Otherwise, go through and find it. Right, while creature pointer current equals this first, current get next creature does not equal the creature with the highest defense. Move to the next one. Because once we find where the next one is, then we want to jump it out of the list. So then currents get next creature, set next creature to the current, get next creature, get next creature. Does that jump it out of the list? So these chains are really annoying to work with sometimes. But so get our next, set the next to the next, right, to take the next out of the list. Because then my next won't be the next anymore. My next will be the next to take out of the list. And if that next is a null pointer, sure, that's fine. Goes and removes out of the list. We do all of that while my first is not a null pointer. And then when we're done, my first can be the new first creature. This one. That using uninitialized memory. It's probably initialized, isn't it?
You give it null.
New first creature.
You give it null and initialize it.
Oh yeah, I have to set it to null. Sure. Because eventually it'll get set to this to the creature with the highest defense for the first time. Then it'll be set to the next ones. That's fine. It should be initialized inside of our code here. I think that it would probably work. All right, all that to add a creature to get the sorted order. Now, this would be easier, I suppose, instead of having to sort, if we just put them in sorted order when we did add creature. But we didn't go that route. Like creature just says, hey, I'll just put them in the chain. So if creature, when you gave it a creature, put it in sorted order, life would have been a whole lot easier. We could have just added the creature and would have added it here. So part of that's just how we went about this one here. Like if you maintain the sorted order, it's just a quick insert here. We could add a set next creature without too much trouble to doing that. Hector, thank you so much for donating to the Student Scholarship Fund, the University of Michigan Dearborn College of Engineering and Computer Science. So if creature had a way to add a creature to the list in sorted order, that just makes life a lot easier for us. So we could have a method in here for adding a creature, right? And I think that would take a lot of that headache out as well. If we just have so if we return a creature reference for add creature, given a creature pointer, creature. So if we're going to add a creature and maintain the sorted order, we can check, hey, if its defense is higher than ours, let's add it first. So we can check and say, hey, if our this get defense is less than the creature's get defense, then we should become the next, although we have to deal with all of its next too, don't we? That's a small pain.
Did you check for the defensive in the thing?
No, we didn't do that yet. No, we only did defense. Yeah, we got to do, if the defenses are the same, then we got to do the strength. We just did highest defense. So if their defense is not less than, I guess we could just do an else if my creatures get defense is equal to the other one. So then it'll be the creature with the highest defense, right, and offense, I suppose. So if the defense matches, then we want the one with the higher offense. So if my current creatures get strength is greater than the creature with highest defense get strength, then we also want to do that. Right, so if the defenses match, then we take the one with the higher strength. I think that'll work. All right, so again, adding a creature, if we did it in sorted order, might be nice, but again, we're not. We'd have to do each one at a time here. So we'd have to go for each creature. We could say creature pointer current equals the creature, and while current is not equal to null pointer, we could loop through, and eventually then we'll take current equals the current next. Right, check the defense. If it's less than, if my defense is less than their defense, then I need to be the new first one. Right, so then I should come after them. But then if it's not, we have to put it in the right location. So I think this might make life a little easier if we finish this one out. But I think this is to do later. Might be easier than doing the whole sort, because it's just going to put in one item at a time, and we'll just add all the items from that list one at a time. I think we can finish that one up later. Is that okay? I don't want to spend too much more time on this one. Nope. That's it. Comment. E and C. Okay, sure. All right. So I think we've got commander, so we can try it and see. Oh, we need battle, right? We didn't do battle yet. That was the last step here. So for battle, so void battle given another commander reference other. So now we need to go in battle, right? So we need to take our creatures. So our first creatures only ever fight first creatures. Then we'll go through, and if we have creatures remaining, we can go and get attacked. So I guess we're going to say while this first does not equal null pointer, and the other first does not equal a null pointer. Other first. There we go. So as long as we're both not null, creatures can fight. Right? So then we can see which ones are going to get killed, right? And then be able to remove creatures as well. So we need to check their strength versus the defense. So yeah.
This is where I ran into the problem. Don't you have to check if one is null first?
So we're going to do that
because I did that. It was checking its strength and defense. We're just crashing because technically it doesn't have a strength or defense because it's null.
Well, so we're checking that they're both not null first. So if both commanders have firsts, then the creatures can fight each other. When this loop is done, then we'll see if anyone has anything left over to do damage to the other commander.
But only has the loop. One of them is null, or one isn't.
Yeah. So if one is null, then no creatures fight each other. It's just my creatures fight you, fight your commander, or your creatures fight me as I'm the commander.
Okay, go ahead.
Okay, so we'll get the so my first creature is going to be. I guess we want the creature. My first is going to be this first, and the creature pointer for other first is other first, and then we can compare them. Right, so we can say if my first get strength is greater than or equal to the other first get defense, then their creatures is going to die.
Here, so let's say my first has a creature, but an other first is null.
It can't be null because we're saying it's not null inside the loop. So the loop won't run if it's null.
Loop will run if they're both
If they're both not null, the loop runs. If either is null, the loop won't run because we're ANDing together here. Yeah, this should catch it, right? If either one of these is null, then the whole thing should be false, right? Because if you are null, not null is false. Anything in false will be false. The loop won't run. So if my strength is greater than their defense, greater than or equal to, they need to die. So we need a way to remove a first. Remove first creature. So to remove a first creature, we'll say this first equals this first's get next creature. Right? You're out of the list. Skip you over. Right? You're gone. So if that's true, then the other commanders remove first creature gets removed. Now I kept the pointer here because I need to be able to compare next now to say if other first get strength is greater than or equal to my defense. My firsts get defense. Right? Otherwise I need to track these separately because once I remove it, if I just go to the other first, I've now changed what their first is. And now I'm not comparing against the same creature. So I kept the pointers around so I can compare the first creatures first. That'll be this remove first creature. Right? And then if none of these are true, so both of these could be true. So we don't want else ifs here, because both of these could be true. Both could happen. Right? Then I want if neither of them are true. So if my first get strength is less than the other firsts get defense. So if my strength is less than their defense and the other firsts get strength was less than my firsts get defense, then I want to break the loop. Because neither creature killed each other, combat just stops. Right? This idea, this just stops the combat. So neither creature died, combat stops. Otherwise you have an infinite loop, right? You'll never be changing the firsts. The first will always not kill each other. Nothing happens. So we need to stop that loop from happening. Right? So once we've killed off all the creatures, one way or the other, or combat stopped, now I can say, hey, if my other dot first is equal to a null pointer, right, and my first does not equal a null pointer, so if I killed all your creatures but not all mine, and this is I still have creatures left. Creatures left to attack. Then I can start doing damage to the other commander. So I'm going to take my creature pointer, the current equals this first. And while current does not equal a null pointer, I can start dealing damage. So I'll take my other, so I need a way to change your hit points, right? I guess in Commander, we didn't have that. So we need a void damage, I guess, in damage. If you had like a set hit points and you did a get hit points, that could work too. Yes, we don't have that get hit points yet either, right? And get hit points, turn this hit points. So I'll just take this hit points and subtract the damage. Again, some sort of sanity checking, making sure we're not doing negative is a good idea, but it's okay here. We can deal with that later, I suppose. So and actually, if we're checking this, we probably don't even need this other part here, right? So just if the other's null, let's see if I have any. If it's not null, other dot damage given current dot get strength, and then walk current. Current equals the current dot get next creature, right? And then the same idea for you still have creatures left to attack. So now if it's this first is a null pointer, it'll be the others first. Starts doing damage to me. This damage. Right? So if you still have creatures, but I don't. So I still have creatures to attack, but you don't. Right? So we're checking if one commander lost all of their creatures or not, then your remaining creatures get to do damage. If it's null, then nothing happens. If it's null, nothing happens. They're just gone. So that's the fighting. The fighting stops when they both survive or they take damage. Sure. So we don't really have a way to see what's happening here. So I know some people added some outputs places to see what was happening. That might be nice. Or like Commander might have a function to list creatures or to print creatures. And that might be nice, like to show what creatures you have. If you want to have a void like print creatures, that might be useful, right? So if we wanted to have that, sure. Again, returning it as a string is probably nicer here. So if you just do a string, get creatures, get creature string or something. I don't know. We can include string. That's probably cleaner here. Include string, and we can use our namespace. Standard. So we can have some sort of string for the results, or I don't know, creature list or something, creatures. And then again, do that sort of loop here. So our creature current equals this first. And while my current does not equal a null pointer, we'll take our creatures and we can append the strength. We could even like do a creature count if you want to, right? We could have an int for creature count. Creature count is 0. So we'll take creature count plus plus creature count. There we go. So a creature number plus the creature count plus the strength plus the current get strength. What am I missing here? Why is it not appending?
If you use
Yeah. Two string of the creature count plus the two string of get strength plus, sure, we'll do all that. That's fine. Defense, the get defense, and then a plus an end line. I guess we can do our own \n, right? Our own new line in there. So this should give me like the list of creatures here. So I could then do that in my main method. I could get my creature string and print it out or see out it here. Include IO stream. And it's nice here if we're not dealing with input and output, because ideally this class can be used anywhere. If you want to make a mobile application or a web application or a graphical user interface application, no one's going to see your CNC out stuff. So you want to avoid classes doing CNC out if you can help it. Covenant for main. All right, now we're going to see if it all works, right? And how much time? We got 5 minutes. Holy crap. All right, we're running short on time here. Do you want to wait to see if it works later when we talk about the final project? Okay, we'll do that because we are running low on time. So let's go back to assignments here. So if you want to work on this in pairs, I'm definitely open to that. I'm not going to require it, but would strongly recommend it. I think you'll get a better product at the end of the day here if you work on this in pairs. So this is going to be due, when was our meeting? Is it the 12th? 11 p.m.? 11 a.m.? I want to say, or 11:30 something? 11:30? That sounds about right. That's 30 points total, right, for 30% here at AutoWork. We set up your repo. So if you do work together, shoot me a message here and I can give you both access to the same repository so you can both make commits to it. You want to make sure you're fetching any changes first, pulling any changes down. So if you both change the same file, Git can get a little confused. It's fixable. It just takes a little bit of finagling with it here. So just let me know. I'm happy to get you set up with that. I just need your GitHub usernames. C plus template. There we go. All right. Let me know are working in pairs, and so both partners need to submit for grading. So if you don't submit here, it doesn't flag it for grading in D2L. So we're going to create a Blackjack program in 3 parts, essentially. So part 1 is the Blackjack classes. Part 2 is the Blackjack game using classes and user input. And then part 3 is going to be building out a prediction model here. So we're going to build a results table to show what strategy loses the least money. So with Blackjack, what? So you don't need to actually count the cards. That's a little more advanced than we want to get to here. But what we want to do, where's my link here, is where to go? So for each starting hand value, either hit or stand and track the result. So the idea here with Blackjack is you want to get to 21 without going over. Okay. Now there's all sorts of other interesting rules. We're going to skip splitting here. We're going to skip double downs here. We're just going to do a basic hit and stand. So you can either hit, means take another card, or you can stand, is take no more cards. So each player plays against the dealer. So the dealer has its own set of rules, and it goes last, is the house's advantage here. So you get 2 cards, and the dealer gets 2 cards, but you only see one of the dealer's cards. So based on what the dealer's card is that you can see here, their face-up card, the ideal strategy based on what your hand total is to either hit or stand. Again, double down, don't worry about that. We can skip that stuff here. What is the best winning strategy for you? So for us to do that is we're going to just play like 10,000 hands and say, okay, well, my face-up value was 13. Out of the 700 times that it happened, half the time I stood, half the time I hit. When I stood, this is how many times I won, this is how many times I lost, this is how many times I drew. When I hit, this is how many times I won, this is how many times I lost, this is how many times I drew. So we should be able to see which one is more successful. Yeah.
What is that?
So that's a surrender, I think, but we don't have that option either. Don't worry about it. Yeah, just if it's not allowed, hit. So this is what is the mathematical solution to it. But we want to build it out and say, let's play the game and have the computer try it here. Because if we can build a model and have it play the game, then we can start doing interesting things with it. So the 3 parts, right, is writing the Blackjack classes. So how do we have a Blackjack hand, right, or play the Blackjack game? How do we see if we win? So the rule here for the dealer is they will always hit until they are 17 or more. So where is it here? So yeah, so once they get 17 or higher, the dealer stops. So if you can get to 17 or higher, so that's why you'll see getting to 17 or higher is usually where you stop. Sometimes you stop a little earlier, sometimes you hit a little later, depending on what their face-up cards are. Because most of the cards in the deck, maybe not most, but there are more 10s in the deck than there are anything else, because jacks are worth 10, queens are worth 10, kings are worth 10. So 4 out of the 13 cards in each suit are 10s. Yeah. Yeah, so aces are worth 1 or 11. So if you are over 21, you want to count your ace as 1. If you're under 21, right, you probably want to count it as 11. So if you have 2 aces, it could be worth 12, right, but not 22, because you would lose. So if you go over 21, you lose automatically, regardless of what happens to the dealer. So that's why the house has an edge. So if you stop at 13 and you just stay, then fine, you stay. If the dealer gets over 13, if they get 17, 18, 19, 20, or 21, they win. But if the dealer busts, if they go over 21, then you win. No matter, so even if you stayed at like 9, if the dealer busts, you win. But you can't bust at 9. So the recommendation is you always hit, right? You always hit at 10. You always hit at 11 because you can't bust here. Once you get to 12, it's possible to bust here. So if the dealer has 14, 15, or 16, the mathematical odds say you should stand because they've got a chance of busting here. Because most of the time, they'll probably have another 10 there. They'll be at 14, 15, or 16. They'll take another card, and then they might bust. But if theirs is a 2 or a 3, you're better off hitting, or if theirs is a higher value, you want to hit because they probably have a 17, 18, 19 or whatever. You want to get to higher than that to win. So the 3 steps, right? Building the classes out here. So we're actually going to have during that last week, I'm over time here. Hopefully you have another second. I want to check in with you folks and make sure you have the classes done during our final project work time. That's sort of your checkpoint. Just to make sure you're getting progress done, because some people leave this to the very last minute and you have other final exams, and then it's a lot of stuff happening here, right? It's involved. So we'll checkpoint, make sure that's done. Then part 2 is just, can I use user input to play the game? So I'll actually ask you, hey, do you want to play the game? So this is sort of how I would test it. Does it work? Right? You can just play the game one-on-one, you versus the dealer. Do you want to hit or stand? It kind of outputs everything. If that works, then we can do part 3, where we're going to simulate like 100,000 hands, and we're going to track our starting hand value, and then randomly pick hit or stand, and track results. Win, loss, draw result. Okay, so at the end of the simulation, display a table showing the results of hitting and standing for each starting value. So the idea is you'll get something, it won't say hit, stand, loss, but it'll say, hey, this is how many times you won, or the percentage of winning. Anyway, you want to show that so we could infer from that data which was the better choice to hit or to stand. Yeah?
So we're only simulating like the one-on-one game, not like the time table of Blackjack. Like,
well, yeah, so that part doesn't matter because everyone plays against the dealer. Players don't play against each other here. And then to do this, we also want, so we want to use a shoe of 6 decks of cards and shuffle the shoe. The shoe gets below, or card count gets less than 100. So the idea is if you just have a single deck of cards when you play, it's really easy for someone to count which cards are there. If you have 6 decks of cards, there's a lot more cards in play. You can still count, but it's not as effective here. So there's a whole movie about it. Some students at MIT went and learned how to count cards and do some interesting stuff there. I forget what it was. Yeah, is that a question?
Yeah. So basically, building deck like play it, and then you're actually playing it. So you're not really, so you're just playing it and see what you get.
So yeah, just playing here is you win, you lost, you win, you lost, you won, you lost. Like how much do you want to bet, right? So tracking bets. You can just say assume every hand is worth $1, right? So we're tracking win, loss, amount, right? So if you win your $1 back. If you lose, you lost that $1. In real blackjack, you can bet more money on different hands, and that's the sort of thing that can give you an edge. If the count's in your favor, you bet more money, but that sort of thing looks suspicious, and the casinos kick you out. Sometimes it's a whole gray area here. But yeah, it's going to say, hey, you play, if you want to play 50 hands worth, you'll say this is how much you won or lost, right? So it's possible to win money in blackjack. The odds are in the dealer's favor, but there are strategies you can use to make those odds a little closer to you winning. So then once we have it working, then we can automate it here to play the 100,000 hands, and just so we want to track here. My starting value was a 7. My starting value was an 8. My starting value was a 9. My starting value was this on and up here. What happened? So half the time just hit, half the time just stand and see what happened. So just do one hit and then to stop there. Because if you had a starting hand of 4 and you hit, and then you say, oh, I want to hit again because now my total's 8, it's going to kind of throw off the results here. Because like now really essentially your starting total was 8. And you hit again. So just a single hit or single stand when we simulate here. Single hit or stand. And then track win, loss, draw. Okay, so we've got Thanksgiving coming up, so no meetings next week at all here. And I'll work on a rubric for you in a little bit. Yeah?
So we're playing 100,000 times. So you want it. I mean, blackjack, you don't really reset the deck every time. You want to reset the deck every time you play.
So we're going to track. So the shoe is 6 decks of cards get all put together in one big stack.
Yeah.
When that gets to less than 100, reset the 6 decks, put it back together. So you have 312 cards again. Yeah, because 52 times 6, right? That's 312. So you start with 312. You can play this many cards out. Once it gets less, you reshuffle it. It's pretty similar to what they do in casinos. Sometimes you use 8 or 10 or different amounts here. So. Less gives you more of an edge as you go. Okay.
So like you're removing the card.
Yeah, so you'll have some sort of data structure that keeps them here and have it efficient. So part of that is going to like be talking about why you picked the data structure you use to store your cards, that sort of thing. How do you store your hand of cards? You know, a little bit of explaining what's happening here, because that's the whole reason why we're talking about data structures and how we store data. Talk about performance impacts. And when we're doing something 100,000 times, it is going to matter. If you pick a slow one, this simulation for 100,000 times will be slow. If you do it right and quick, you can run it in, you know, a few seconds.
So because everybody should be doing the same thing in our presentation, explaining like why we chose to do certain parts of the
You're pretty much going to show, you'll play a hand in part 2, and then you'll show part 3 results. And then I'd say, hey, you know, show me in your code what it does here. It's 5 to 10 minutes. 10 is way tops. Usually it's 5 minutes or less. Yep. So everyone will show, you know, play a hand in part 2, and then show their part 3. Here's your results. And everyone should have pretty similar results. If yours are way different than someone else's, you probably have a bug. Right? If yours look way different than this, you probably have a bug. Okay. Sorry to keep you over. I apologize for that. Commander took a little longer than I thought. That's a fun one. So thank you so much. Have a great Thanksgiving, and I will see you in late November.